you were to slice open a modern CPU and GPU and peer inside with an electron microscope, you'd see two completely different philosophies etched in silicon. Both chips might have billions of transistors, but they spend their transistor budgets in radically different ways. Let me show you how. Meet the CPU, the Central Processing Unit. It's designed for low latency and rapid sequential execution, optimized to handle diverse tasks with minimal delay. Notice how it dedicates enormous amounts of silicon to L3 cache, sometimes up to 50% of the die area, all to keep data close to the cores and avoid memory bottlenecks. And see this complex control logic? Branch predictors, instruction decoders, out-of-order execution units. Sophisticated circuitry that keeps a few powerful cores fed with work. The result? A handful of incredibly capable cores, typically 4 to 16, that can tackle almost any computational challenge you throw at them, never starving for instructions. Now, in stark contrast, the GPU is an absolute beast of throughput. Where the CPU says, "I'll handle this carefully," the GPU says, "Give me everything at once." It deliberately strips away most of that heavy management overhead. The elaborate branch prediction, the complex control logic, trading single-thread speed for massive parallelism. And with all that freed up space, it packs in thousands upon thousands of tiny, simple cores. A modern GPU might have over 10,000 CUDA cores, each one a lean, mean calculating machine. It's like tiling the entire chip surface with pure mathematical horsepower. An army of specialized workers, all executing the same instructions on different data simultaneously. When we actually visualize how these chips allocate their silicon real estate, the architectural philosophy becomes crystal clear. The difference is absolutely stark. These pie charts reveal two fundamentally opposed design strategies for the same goal: computation. While the CPU invests nearly half its precious silicon budget just on cache memory and another 30% on control and scheduling logic, leaving only 10 to 20% for actual compute units, the GPU flips this completely around. A staggering 80% of its area is dedicated to raw calculation. The ALUs, the floating point units, the execution pipelines. This is the key insight. GPUs sacrifice per-thread intelligence to maximize parallel throughput. They dedicate their silicon to math, not management. And for workloads that can be parallelized, like graphics, AI training, or scientific simulation, this makes all the difference.